Welcome to Spring LIB.
Hi everyone, so what we have here is a rocket that's in initially a circular orbit around the Earth, and what we're asked to do is solve for first the speed at A, as shown here, and we're also required to solve for the change in speed, or the delta V at A, that's required so we can go from that circular orbit into the elliptical orbit that's shown here. And I actually need to change this. So this is the problem statement that we have here. We see that the radius of the circular orbit is 8 megameters, and the distance from A prime to the surface of the Earth is 19 megameters. And the concepts that we're going to use to solve this problem is our knowledge of orbital dynamics and also orbital mechanics as well. So let's go ahead and solve this problem. So what we need to do is first determine the speed that's required to stay at the circular orbit containing A. So we know that R naught, which is going to be a radius, is going to be equal to the radius of the Earth plus the distance from the surface of the Earth to point A. We're just going to call that RE. And plugging in the quantities that we know that R naught is equal to 14.38 times 10 to the 6 meters. We can directly solve for our velocity at C, or velocity at A, and that's we're going to denote as VAC for circular, and that's going to be equal to the square root of GME all over R naught. And plugging in all of these quantities, we get a VA for the circular orbit to be equal to 5.3 times 10 to the third meters per second. Next, what we're going to do is we're going to look at the point A prime. So to move from A to A prime, the rocket has to follow the elliptical orbit with RP, which is equal to 8 times 10 to the 6th, plus the radius of the Earth, which is equal to 14.4 times 10 to the 6th, and RA, which is equal to 19 times 10 to the 6th, plus RE, which gives us 25.4 times 10 to the 6th. Therefore, we can compute our required speed at A to jump from the circular orbit to the elliptical orbit. What we can do is we can say that RA is equal to RP all over 2GME all over RP VP squared minus 1. And what we're going to do here is we're going to isolate VP. We're going to see that VP is going to be equal to the square root of 2GMERA all over RP times the quantity RP plus RA. Then what we see here is that VP is actually VA for an elliptical orbit. And by plugging in for all of these quantities in this equation, we see that the VE for an elliptical orbit is equal to 5950.6 meters per second. Therefore, we can compute our delta V by saying that our delta V is equal to VA for the ellipse minus the velocity at A for the circular orbit, and this gives us a delta V required of 684 meters per second, and that's our final answer.